Okay, good morning, everyone. I hope you're all doing well and staying happy and healthy and managing to stay on top of all of your coursework. So I just wanted to talk a little bit about the deliverables before we jump back into lecture. I assume you all can hear me. If so, please just type yes into chat. Sometimes hard to know whether you're all there. Okay, great. Okay, so hopefully all of you managed to submit Deliverable 4 on time last night. Just a couple of notes about Deliverable 4. Some of you pointed out that your visualization sometimes it's updating after it seems like it's done. So sometimes you'll see one or two of your dots that are blinking back and forth, or at least the edge of the circle is blinking between different colors. Remember that at the end of Deliverable 4, you're using P5's draw loop. So every time it goes to refresh the screen, it enters that function called draw and does everything that's in that function, and then repeats. Inside that draw function, you're drawing each of the 150 circles, but you're also generating test predictions. So it's filling in different predictions in that vector at the same time that it's drawing. So the predictions and the drawing is a little bit out of sync. So you might see a little bit of changes in what should be ultimately a static image. If you saw that, that's perfectly fine. It is not going to affect your grade for Deliverable 4. If you got to the end of Deliverable 4, you know that you're submitting a screenshot and not a video. What we're looking for in that screenshot is that most of the predictions, but not all of the predictions from your KNN are correct. Any questions or confusion about Deliverable 4 before we talk about Deliverable 5 for a minute? All good? Okay, so you're moving on to Deliverable 5 today. And as I mentioned a few times, but just to keep the big picture straight in your mind before you dive back into the details, in Deliverables 1, 2, and 3, you were setting up some code that was able to grab a frame of data from Leap Motion and store it in a 3D tensor, right? Basically a cube data structure that has 5 rows corresponding to the 5 fingers, 4 columns corresponding to each of the 4 bones in each of the 4 fingers, and then 6 horizontal sheets or stacks that are storing each of the 6 coordinates associated with each of the 20 bones in the human hand. So for every frame of data, we're throwing everything away except those 120 numbers. In Deliverable 4, you set up your KNN classifier that takes as input 4 features and outputs an integer between 0, 1, 2, 3, 0, 1, 2, or 3, the prediction about the species of that iris. In Deliverable 5, you're going to be integrating your capturing and recording of frames of data from Leap with your KNN algorithm. Going to be basically the focus of Deliverable 5 is integration. This is when you're going to start to sign ASL digits, and you're going to be feeding those 120 numbers from a potential sign. You're going to be feeding those 120 numbers into your KNN, and it is going to produce as output an integer in the range 0 through 9, which is the KNN's prediction of which of the 10 digits is currently being signed over the device. Okay, so we're going to sneak up on this, and the way we're going to do this is each of you is going to be assigned 2 digits to start with, and by the end of Deliverable 5, your KNN should be able to take in a frame of data and predict which of your 2 digits is contained in that frame. So at the end, you're going to be capturing some test data that contains, for example, the digits 6 and 7. Feed that. You're going to collect test data that contains you signing 6 and 7, and then you're going to run your KNN, and you'll see it predicting, alternating between 6 and 7. So at the end, what we're looking for is a KNN that is sometimes predicting one of your digits and sometimes predicting the other digit. which will convince us that you've trained it on these two different classes, these two different digits. By the end of Deliverable 5, you will not know how accurate your KNN algorithm is. That we're going to tackle in Deliverable 6. At the beginning of Deliverable 6 next week, you're going to set up your KNN so you can see its prediction accuracy. How many for multiple frames of data did it get right for 2 of your digits? Then you're going to fold in data from another student, so you have 3 digits. You're going to see how well your algorithm does at those 3 digits, 4 digits, 5, and at the end of Deliverable 6, at the end of next week, you will have a KNN that can predict any of the 10 digits. Okay, last thing I want to say about Deliverable 5 is at the end, you're going to be submitting this week not just some videos. You're actually going to be submitting 1 screenshot. You're going to be submitting 2 videos, and you're also going to be attaching to your submission in Blackboard 2 files, train X and train Y. In each of those files is the definition of a variable, which is frames of data for your digit X from you, and a variable that stores data about the second digit from you. So we're going to be collecting at the end of Deliverable 5 data from all of you for your 2 digits. We're going to combine that into one big data set. And at the beginning of next week, Deliverable 6, you'll be downloading a zip file that contains it will contain a total of 60 students times 2 files each. That zip file will contain 120 files. Each file contains a tensor, so you'll be downloading a data set that contains 120 tensors, and you'll be training your KNN on an increasing number of those 120 tensors in Deliverable 6. Okay, that's to try and give you the big picture of where we're going. Deliverable 5, you're integrating, capturing data with your KNN. Any questions about big picture deliverable stuff before we get back to lecture? So far, so good? Okay, Deliverable 5 is pretty long. I think it's probably the longest of all the 10 deliverables. So as always, I recommend you get started early on the deliverables, but I particularly emphasize trying to get started early on Deliverable 5 this week to give yourself plenty of time to work on it and plenty of opportunity if you get stuck to come and see Amanda or I during our office hours. Okay, so where are we? We did not quite finish Lecture 6 last time, so we'll carry on with Lecture 6 today, where we were focusing on a particular aspect of HCI design, which is visual design. Humans are visual creatures. We extract most of the information from our technologies through our eyes. How do we take the massive amounts of data that are out there and the growing amounts of data from year to year and find creative and useful ways to compress that data, communicate it to the user in a way that is useful or acceptable to them. Okay, we will then, we'll probably start Lecture 7 today, which is looking at the design process. Once we know what the user need is, how do we gradually turn that into an interactive technology? So we've talked a little bit about philosophy, design principles. We took a detour into visual design. Now in 7 and 8, we're going to get into the design process itself and how that differs from the typical design process in software engineering. Okay, so back to Lecture 6. We got to, where did we get to last time? We got to our introduction of Hans Rosling, the creator of Gapminder, and as you know, Gapminder is sort of a running example throughout this course. We were partway through his TED Talk, and we'll watch the last few minutes of his TED Talk in a moment. Just as a reminder, what I asked you to do as you're watching this video is to write down details of 4 different aspects of the way in which he presents Gapminder. He talks about a lot of conceptual or abstract concepts: gross national product, the spread of disease, education issues, things that can't actually be touched. but he concretizes them or makes them concrete using various kinds of graphs and animations and figures. And in each of those graphs and animations, he uses a number of visual constructs, circle areas, heights, movement, and so on. He brings these three things together to create visual metaphors. What has been changing in terms of health and wealth in various nation states over the last 20, 30 years? You actually hear him mention some of these metaphors in his talk. Okay, so back to the TED Talk. We had about 7 minutes left, so I will start it there. When I start the video, please let me know whether you can hear the audio on the video by just typing in, I can hear the video.
Again here, and we put on trails on them like this. You can see again that the speed of development is very, very different. And the countries are moving more or less in the same rate as money and health. But it seems you can move much faster if you are healthy first than if you are wealthy first. And to show that, you can put on the way of United Arab Emirates. They came from here, a mineral country. They catch all the oil, they got all the money, but health cannot be bought at the supermarket. You have to invest in health. You have to get kids into schooling. You have to train health staff. You have to educate the population. And Sheikh Zayed did that in a fairly good way. And in spite of falling oil prices, he brought this country up here. So we got a much more mainstream appearance of the world, where all countries tend to use their money better than they used in the past. Now, this is more or less if you look at average data of the countries. They are like this. Now, that's dangerous to use average data because there's such a lot of difference within countries. So if I go and look here, we can see that Uganda, that today is where South Korea was 1960. If I split Uganda, there's quite a difference within Uganda. These are the quintiles of Uganda. The richest 20% of Ugandans are there, the poorest are down there. If I split South Africa, it's like this. And if I go down and look at Niger, where there was such a terrible famine lastly, it's like this. The 20% poorest of Niger is out here, and the 20% richest of South Africa is there, and yet we tend to discuss on what solutions there should be in Africa. Everything in this world exists in Africa. And you can't discuss universal access to HIV for that quintile up here with the same strategy as down here. The improvement of the world must be highly contextualized. And it's not relevant to have it on regional level. We must be much more detailed. We find that students get very excited when they can use this. And even more policymakers and the corporate sectors would like to see how the world is changing. Now, why doesn't this take place? Why are we not using the data we have? We have data in the United Nations, in the national statistical agencies, and in universities and other non-governmental organizations, because the data is hidden down in the databases. And the public is there, and the internet is there, but we have still not used it effectively. All that information we saw changing in the world does not include publicly funded statistics. There are some web pages like this, but they take some nourishment down from the databases, but people put prices on them, stupid passwords and boring statistics. And this won't work. So what is needed? We have the databases. It's not a new database you need. We have wonderful design tools, and more are added up here. So we started a non-profit venture, which we called Linking Data to Design. We call it Gapminder, from London Underground, where they warn you, mind the gap. So we thought Gapminder was appropriate. And we started to write software which could link the data like this. And it wasn't that difficult. It took some person years, and we have produced animations. You can take a data set and put it there. We are liberating UN data. Some few UN organizations, some countries accept that their databases can go out on the world. But what we really need is, of course, a search function. A search function where we can copy the data up to a searchable format and get it out in the world. And what do we hear when we go around? I've done anthropology on the main statistical units. Everyone says it's impossible. This can't be done. Our information is so peculiar and detailed, so that cannot be searched as other can be searched. We cannot give the data free to the students, free to the entrepreneurs of the world. But this is what we would like to see, isn't it? The publicly funded data is down here, and we would like flowers to grow out on the net. And one of the crucial points is to make them searchable, and then people can use the different design tool to animate it there. And I have a pretty good news for you. I have a good news that the present new head of UN Statistics, he doesn't say it's impossible. He only says we can't do it. And that's a quite clever guy. Huh? So we can see a lot happening in data in the coming years. We will be able to look at income distributions in completely new ways. This is the income distribution of China, 1970. This is the income distribution of the United States, 1970. Almost no overlap. Almost no overlap. And what has happened? What has happened is this. That China is growing, it's not so equal any longer, and it's appearing here, overlooking the United States, almost like a ghost, isn't it? Huh? It's pretty scary. But I think it's very important to have all this information. We need really to see it. And instead of looking at this, I would like to end up by showing the internet users per 1,000. In this software, we access about 500 variables from all the countries quite easily. It takes some time to change for this, but on the axes, you can quite easily get any variable you would like to have. And the thing would be to get up the databases free, to get them searchable, and with a second click to get them into the graphic formats where you can instantly understand them. Now the statisticians doesn't like it because they say that this will not show the reality. We have to have statistical analytical methods, but this is hypothesis generating. I end now with a world there the internet are coming, the number of internet users are going up like this. This is the GDP per capita, and it's a new technology coming in, but amazingly how well it fits to the economy of the countries. That's why the $100 computer will be so important. But it's a nice tendency. It's as if the world is flattening off, isn't it? These countries are lifting more than the economy. It will be very interesting to follow this over the year, as I would like you to be able to do with all the publicly funded data. Thank you very much.
Okay, so what were some of the visual metaphors that Rosling talked about in his presentation, and what were some of the visual constructs and abstract concepts that he was bringing together in those metaphors? If it's easier to unmute yourself and just speak, that's fine too, or type things into chat. Either is fine. I mentioned actually one of these metaphors, or I put one of these metaphors on your quiz from last Thursday, and I realized that particular metaphor that was on the quiz last Thursday only showed up in the video today. I'm sorry if that was a little confusing, but I think it should have been relatively clear. What was that metaphor? Yep, so David mentioned the bursting of the bubbles, right? So this the verb to burst here. What is the point that he is trying to make with this metaphor? There was the literal bursting of circles in the animation, of the bursting of these visual constructs. But what was the connection in the metaphor with an abstract concept? What was really being burst here? Average data can be very misleading, right? He was trying to burst or pop or deflate our intuitions about, in his case, Africa, right? That there should be one solution for Africa. We assume when we see a circle or we see something on the screen that is, at least in Gapminder, representing an average, there is an assumption that the standard deviation underlying that average, the spread of the data, is relatively narrow. It's just sort of a simplifying assumptions that humans tend to make, but that is not necessarily the case. Remember that when we started to talk about visual design, one of the things we have to do when we're visualizing large amounts of data is simplify somehow. So in Gapminder, most of the time you're seeing averages, but not standard deviations. And often the standard deviation is as important, if not more important, than the mean. So when we dig down into the data and we break open the bubble, the mean, and look at the standard deviation, gives us a very different picture of the distribution of health and wealth in countries. Amanda mentioned the metaphor of lifting up, right? This old metaphor in English of lifting people out of poverty. Up is usually good and down is usually bad, in English at least, again for cultural and social reasons. Usually lifting someone or something up usually means improving and not making it worse. That is an assumption in a lot of the language that we use and the way that we graph data. You'll notice life expectancy increases on the vertical axis. Longer life is better. Up is better. Okay. He mentioned towards the end of the talk this idea of data liberation. So we have more and more data out there, but it is not necessarily all accessible. The TED Talk that we watched today, it was sort of talking about the recent history of health and wealth in various countries, and that TED Talk itself is also now a historical document. It's from the early 2000s. Professor Rosling recorded several more recent TED Talks that you can go and watch if you're interested in this topic. So he was talking about his group's efforts to liberate data from UN databases. Has the data revolution come to pass, or the open data revolution? Is it easier to access data now about, for example, health and wealth than it was in the early 2000s or mid-2000s? One of the particular statistics that many people are interested at the moment is the current spread and state of COVID in various countries. If I asked you to send me a spreadsheet that had data about socioeconomic status in Spain and the spread of COVID in Spain, how easy would it be for you to find that data, extract that data, and then supply it to me in a spreadsheet? There's a wealth of COVID spreadsheets, dashboards that are out there at the moment, but how open are those dashboards? How easy is it to extract raw data about perhaps not just COVID, but the relationship of COVID to other health and wealth indicators or socioeconomic status indicators in those countries? Is data more open now than it was as it was in the mid-2000s, as described by Professor Rosling? Some of you may be busy in a browser right now trying to answer that question. So Sarah says more open now. I think things are better. I think things are better than they used to be. There's certainly a lot more tools out there. So again, if you're interested in this topic, it's worthwhile trying to do some exploratory data dives to see how true that is. One of the things that may be particular to our particular group is how well are various campuses in the United States dealing with COVID outbreaks. UVM is getting a good reputation for doing relatively well. Is there a ranking out there? Could you download a ranking in comma-separated in a CSV file? How open is that data? Obviously, this is data that is emerging from week to week and day to day. How accessible is it to rank campuses by their ability to reconcile with the pandemic. So as Amanda says, it's better, but maybe not completely. For many things, it is still hard to get access to the raw data itself. There are many more dashboards that present the data, but don't necessarily make it available. Okay, so let's move on. The rest of Lecture 6 today is going to be broken into 3 different subjects, and those 3 subjects are drawn from 3 different books written by Edward Tufte. Tufte is sort of the founding person of the field of graphic design. He wrote 3 very popular books on this. For anyone who's interested in the graphic arts or visual design, these are 3 books that you should absolutely have on your bookshelf. Tufte himself summarized his 3 books as pictures of numbers, then pictures of nouns, and pictures of verbs. So the visual display of quantitative information, which I have here somewhere, is about, as he described it, pictures of numbers. So strategies for trying to visualize abstract concepts, things that don't exist out in the world to touch. And the Gapminder website is an example of trying to do that well. We'll talk about some of the strategies of visualizing abstract concepts in a moment. His second book was about pictures of nouns, actual things that existed in the world. And his last book, Visual Explanations, was about pictures of verbs, action, things that unfold over time. How do we create static images or visualizations of things that are changing over time? Visualizing these 3 different kinds of things, abstract concepts, concrete things that exist in the world, and things that change over time, the way in which users want to understand those 3 different kinds of concepts informs how we go about trying to display them to the user. He also wrote a very interesting and thought-provoking book on the cognitive style of PowerPoint and how these days we communicate we communicate lots of information presentations through PowerPoint, which itself influences the way that we try and communicate information. Okay, not so relevant to HCI, but an interesting read for those of you that are interested in those kinds of ideas. Okay, so let's start with Tufte's most famous book, The Visual Display of Quantitative Information. This is about trying to graph information. And as we've already talked about, one strategy is to find clever ways to summarize, but not summarize too much. Right? We might want to start by presenting a visualization that shows the means of data sets, like in Gapminder, but also provide the ability for the user to quote unquote reach into the visualization and see and remove some of the summarization. So look at the standard deviation, for example. If we're assuming that this is a static image, then of course the user doesn't have that opportunity. Usually in HCI, you're creating interactive graphics, which means the user is doing something. What are they doing? They are manipulating or changing a visualization to perform an activity, which is usually trying to reason about the information that is being presented. Given the fact that they're observing the data, they may start to form hypotheses about relationships among those data sets. How do they know whether their hypothesis is correct or not? They can perhaps go in and try and prove or disprove their hypothesis by looking at other parts of the data. So for example, we might click on a country bubble and it breaks into the quintiles, the bottom fifth and top fifth and middle fifths of that data, and notice that the standard deviation is very broad. That might lead to the hypothesis that that standard distribution in health or wealth in a given country is similarly wide in other countries. That's a hypothesis. I can test that hypothesis by popping other bubbles and see how much the spread exists in those bubbles as well. I might notice that spread is very wide in some countries and narrow in others, which is evidence disproving my reasoning. So as everything in HCI, we have this feedback loop where the user is acting on the visualization, in this case popping bubbles, and observing the results of their actions, right? Observing how the world pushes back, or in this case, how the visualization pushes back. So we're trying to create usually not just visualizations, but interactive visualizations that allow users to test their hypotheses about that information. Okay. So how do we do that? How do we start with the summarization and then make it easier for the user to gradually unfold or reveal more data as they go? Let's take again an example from Gapminder. As we know now, Gapminder has lots of information about different kinds of health and wealth indicators. So, and you can plot any two of them against one another in Gapminder. In this case, in the inner axes here, you can see we have a health indicator on the vertical axis, life expectancy, and we have a wealth indicator on the horizontal axis here. But there is also other indicators like pollution rates, so carbon dioxide emissions per capita, total population, which is actually shown by the size of the circles. But there's, I don't know how many different health or wealth indicators in Gapminder. What if we wanted to plot or compare not just life expectancy and GNP, but what if we wanted to compare life expectancy and GNP and CO2 emissions? Naively, we might try and create a 3D plot where we have three axes for those three dimensions of health and wealth indicators, but that's probably not going to work very well, given what the user is going to want to do, which is to try and see, are there relationships between these? We can see that for life expectancy and GNP, there's a positive correlation. There's a positive correlation between these two. Is there a correlation between the three of them? We could try and draw this in 3D to help the user see whether there is this three-way correlation, but that's probably not a good choice. Why going to a 3D visualization? Why might going to a 3D visualization might not be a good choice? Why might it frustrate this particular activity, looking for three-way correlation, then facilitate it? Imagine a 3D plot with these three vectors, and we now have not circles but spheres existing in three-dimensional space, being drawn in a two-dimensional screen. What's the problem with 3D visualization? Hard to compare size of the spheres, especially with a 2D representation. Yeah. So when we go to 3D, exactly. So if a sphere is smaller towards the back of this cube, if we're drawing in 3 dimensions, is that circle smaller because the population is smaller, or did the person who created the visualization shrink circles that are further away to help with the illusion of 3D, right? That could be a little confusing. Good point. What's the other problem with 3D? You had to deal with this when you were drawing virtual hands, which we actually tried to turn to our advantage. Some of you may have struggled a little bit with occlusion, right? Remember, some of the distal fingers need to be drawn, proximal bones need to be drawn over top of distal bones. If you're drawing in 3D, it's difficult because occlusion becomes a bigger problem, right? Certain things are behind other things. One of the ideas that Tufte introduced in his book is this idea of a rug plot, so a different kind of visualization, which does not draw in 3D, so it minimizes occlusion, which is a good thing, and it's designed to try and help you see correlations between more than 2 features. Okay, so let's start in the upper left panel here. We have child mortality, so a health indicator on the vertical axis here. In this case, further up is bad, so this is actually an exception to the rule we were talking about before. GNP on the horizontal axis here, and we can see an inverse relationship between child mortality and GNP, which makes sense. You'll notice that the vertical axis here, child mortality, is copied on the top right panel here, and then we add a third axis here, carbon dioxide. So if you flip back and forth between these two panels, you can ask yourself whether there is a three-way correlation between child mortality, GNP, and CO2. You should be able to see that as countries become more wealthy, meaning they move along this horizontal axis, child mortality drops, and as child mortality drops, carbon dioxide increases. So richer countries tend to be more polluting and have lower child mortality. Okay, we can keep going by adding on additional panels and copying one of the two dimensions into the new panel. So if we go down to the lower left, you can see that GNP is copied on the horizontal axis, and we've added a fourth dimension on the vertical axis in the panel in the lower left. And again, as we would expect, more richer countries have higher life expectancy. Okay, we could argue about the pros and cons of this visualization versus the 3D visualization. The point here is this one was designed to try and deal with a problem with 3D visualization, which is occlusion. So minimize occlusion. This visualization is designed to help you try and see multiple relationships in more than two dimensions. You might be able to think up other visualizations that are easy to draw in 2D, but also help the user see whether there are relationships between more than two variables. You can probably guess why it's called a rug plot. We have a bunch of these panels, and they look like they have these threads coming out between the panels, which are one-dimensional projections. So you can see child mortality here. Each one of these threads between the panels is representing child mortality in a particular country. And by looking at just the threads, we can see some additional information about this data set, which is the distribution of child mortality across these countries in, I see these are different years, should be about the same, around the same time. Right? So a lot of information, there's a lot of information in this particular rug plot. You may not be able to absorb all of it at one time, but it is, again, an attempt to try and maximize the data to ink ratio. We're trying to communicate a lot of data with as little ink as possible. Okay. Let's think about a different activity, trying to look for patterns in the global financial market, and a different visualization tool, or a different kind of visualization designed to help with seeing patterns in a hierarchical data set. So unlike Gapminder, health and wealth of countries, countries are relatively flat. The financial market is hierarchical in the sense that we have the global economy, which is this entire rectangle. Inside the global market are various sectors of the economy represented by these large black rectangles. Inside each sector, we have various companies represented by the smaller rectangles. So this is known as a tree map visualization. You can go to finviz.com and interact with this visualization. A tree map is a good way to visualize hierarchical information. I guess we could argue that countries are also hierarchical. We have the globe as a whole. We have individual countries. Countries are broken up into provinces and states and cantons and cities and so on. So we could, I guess, use a tree map visualization as well. As usual, there is a lot of things going on in this visualization, and since it is designed well, at least according to most people, most of what's going on here doesn't require an additional legend that describes what's going on. What do the sizes of the rectangles represent? It doesn't actually say here, but hopefully you can guess. What do the size of rectangles represent? Not stock price. Market cap, okay, that's close. Market share, right? So what are the size of the companies economically? You should be able to spot some of them here. What are some of the obvious big players here? There's hints from their stock exchange names. So Microsoft, very clear, yeah. What are some of the other large rectangles here? Yeah, Apple is clearly visible. You'll notice that for the large rectangles and also for the small rectangles, their aspect ratio is relatively balanced, meaning we don't have very long, thin rectangles or very tall and thin rectangles. It's a relatively complex algorithm that produces this tree map visualization. And again, this seems like a detail. In this algorithm, it tries to keep the boxes as close to a square as possible. Why? That decision is meant to support an activity that you may do when you're looking at this visualization. What are the things you might want to know about the market at a given point in time, which this is a snapshot of? How does keeping the comparing size exactly, right? So you can probably see, for example, that Google is slightly bigger than Facebook. And Microsoft and Apple, actually, that's a hard one to tell, right? If we had very large aspect ratios, very long and thin rectangles, it would be harder to visually inspect two given rectangles and tell which one has more market share than the other. Okay, color is a little more obvious. What does color represent here? Mario says negative markets, right? So I think I took this screenshot. This was actually for, yeah, right. So it's showing whether the company has been more profitable as gained in shares or lost in shares over a certain time period. And I forget what time period I put into FinViz when I took this snapshot. What else can you learn about the global financial market during this time period, aside from which companies are bigger than which companies were doing well and which were doing poorly during this time period? What other information is hidden in this visualization? What other hypotheses or questions can you ask about the structure of the global market, which you can see hints about in this visualization? The sizes and strengths of different industries, right? You'll notice that the technology market, especially if we combine the technology market in the upper left with the communication services in the upper middle, they are together much larger than, for example, financial or energy used to be one of the big ones down here. It's small now compared to technology. This is a huge change over the last few decades, right? With the advent of computer technology, it was the creation of an entirely new sector of the economy, which is now the largest sector of the economy. If we take any given sector, we can ask about the distribution of sizes of companies in that sector. This is something that is relatively easy to see in a hierarchical visualization like a tree map. As you can see in the case of technology, Microsoft and Apple are massive, and they take up, let's say, maybe a third of the entire technology sector. Whereas if we go to the financial services, the two largest companies here take up much less than 1/4 of the entire financial market. So we can get an idea about distribution, something we just talked about in Gapminder, in this way as well. So this is just meant to represent what is it that someone is trying to do when they view or interact with a given data set. What is the structure of that data set, and how does that inform the way that we might go about creating visualizations for them? Okay, so again, some of those challenges have to do with the fact that we're dealing with abstract concepts, prices, corporations, health and wealth indicators in countries. Let's talk about creating pictures of nouns now. We assume that we have a distribution of objects or things out in the world. They are, quote unquote, lying on the ground. They have physical positions in the world, and we want to try and create a visual representation of them. One of the things that distinguishes visualizations of physical objects from abstract concepts is that now we need to decide on a correspondence between the actual spatial arrangement of those objects out in the world and the spatial arrangement in the visualization itself. So this is a long roundabout way of saying that we're dealing with maps in this case. Every single map that's ever been created is not a one-to-one correspondence with the thing that is being mapped. If it was, if we had a map of the globe, if there was a one-to-one correspondence, that map would be the same size as the globe. Not very useful, right? Okay, so we're obviously going to take the spatial one of the things we're doing when we're creating map visualizations is shrinking the spatial arrangement for obvious reasons. But there are other transformations or other alterations to the correspondence between the actual organization in the world and the spatial organization and the visualization. Other transformations of the coordinate system that we're going to include, again, based on what people are trying to do with that data. So let's have a look at an example. This is the lecture in which the London Underground is actually mentioned twice. This is the second time you've heard about the London Underground today. Okay, here's a one-to-one, not quite a one-to-one map because it's not the same size as downtown London, but it is close to a one-to-one correspondence between the actual spatial arrangement of, in this case, London Underground stations. I want you to look at this visualization and figure out what is the best way to get from Burrell Station in the lower right to Warwick Avenue in the top left. For those of you that know the London Underground, that's fine. For those of you that don't, you'll notice that the different lines are different colors. Which lines would you visit to most easily travel between the red station and the purple station? If you have an idea, go ahead and type it into chat. Okay, Bryce has got the right idea here. We're going to go south on the black line to start and then switch on to the light brown line, which will take us eventually to Warwick Avenue. Okay. Why is that the best route? There are other routes. I asked you to perform a particular activity, which is to find the best route. What is the definition of a best route when you're using a subway or a train network or the London Underground? What is meant by best? The least amount of switching. So if we look at this picture, I don't know if there is, but as the crow flies, if we wanted to take a shorter overall distance, there might be an alternate route. I'm not sure if that's true. So whether you were aware of it or not, the activity that you were conducting is to try and find a route between the red and the purple station using the minimum number of switches. This particular map is not well suited to performing that activity. This map is much better for performing that activity. I'll give you a minute to just have a look at this, and hopefully it's much clearer to you now about which of the many routes between Burrell Station and Warwick Avenue, which of the many routes has the minimum number of switches. And as Bryce mentioned, it is indeed going from the Northern Line in black to the Bakerloo line in brown. As you can see, there are a lot of simplifications that were made from this map to this map. The map of the London Underground is probably the most famous example in the field of visual design for obvious reasons. There are many, many design decisions that are built into this particular visualization that are meant to help with a very particular activity, which is figuring out the best route between point A and point B on a relatively complicated underground system that is underneath a relatively complicated city. What are some of the design decisions that are built in here that are meant to help support that task? How is this visualization different from this visualization? And why were those differences built in? As Cole mentions, there's more straight lines. So the particular curvatures, the particular local curvatures of the particular routes is irrelevant from the point of view of someone who is just trying to figure out their commute. They have removed a particular detail of the system that is irrelevant to the task. Matthew mentions clean turns. What are meant by clean turns? Jillian mentions they've eliminated street signs. Again, if I've chosen to go on the underground, then the actual layout of streets doesn't really matter. A lot of detail has been removed in this image compared to this image, but there are also some additional details that are built in. There are some things you can see in this visualization that are not shown here. Why was some detail added? And how is that useful for the task of figuring out how to commute in London? You'll notice that there's this sort of bullseye pattern of alternating gray and white. So the names of stations, are here, and they're kind of here, but they're kind of hard to read because there's obviously a lot of detail here. So the names have been clarified. That's obviously important. What about these alternating circles of white and gray? Why were they added, and what aspect of the activity are they meant to support? The most important thing is, again, minimizing the number of switches. But in a complicated network like this, that is not the only thing that a commuter or a traveler is trying to optimize as they travel. It may be hard to read, but in the legend down here, it's mentioning zones A, B, and C, zone 1, 2, 3 through 6. So you'll see zone 1 in the center here, surrounded by zone 2, 3, 4, 5, 6, and then A, B, C out here. Minimizing cost, absolutely. So traveling in outer zones is cheaper than traveling in inner zones. And you can imagine why that's the case. So one of the things depending on how complicated your route is, you're trying to minimize travel time, but also minimize cost. And as you're considering alternative routes, it helps to know the cost zones as well. You'll notice also that the relative positions of the stations have been moved, right? So if you look at the pairwise distances between stations here, that's closer to reality than the pairwise distances between stations here. So for example, if we go right in the center and look at this relatively short distance between Oxford Circus and Bond Street, that might not actually be true. Those two stations might physically be far apart in reality, and vice versa. Some of the longer seeming distances in this visualization, those stations are actually closer to one another in reality. why would you actually make this less? Why would you move the relative positions of the stations? Seems like an odd design choice to make. So Amanda mentioned that it's relatively easier to read the names of stations on this picture. If we actually bunched up some of the stations where they actually exist bunched up in reality, it's harder to add the legends to the names. So by spreading out the stations a bit, at least in the inner zone, so that the distribution of stations is more uniform than it is in reality, it's easier to label all of the stations. You'll notice the Leicester Square note down here is relatively close to these four. It could be difficult to see which particular name corresponds to which particular station if they were bunched up. So by making things more uniform, it becomes easier to read which station is which and solve the task of how best to get from point A to point B. Okay. Let's move on to Tufte's third book, which is about pictures of verbs, actions, or things that unfold over time. These could be mechanism, motion, process, dynamics, cause and effect. A does something and causes B to do something, which leads to explanation about why things change over time, and help with a narrative. This happened, then this caused this to happen, and so on. We could obviously create an animation to correspond to something that is unfolding in time, and we can borrow some of the ideas from pictures of nouns, where the spatial correspondence between physical objects is warped from the actual spatial distribution in reality, and do the same thing with time. So if we have things that are unfolding over time at differing rates, we might show those differing rates in an animation, but simplify those differing rates to again help people to reason about what's going on in these phenomena that are changing over time. We might, for example, a user might be trying to figure out whether A is unfolding faster than B, but they don't care about the actual difference in velocities between these things. They just want to know which is faster than which, in the same way that we might just want to know which is a better route from point A to point B. So we might simplify things a little bit to make it easier for people to see which phenomenon is unfolding faster than another one. In the same way also that we might have wanted to see which company is bigger than another one, but we don't need to actually visually estimate how big in actuality Microsoft is. We don't care about absolutes, just relatives. Which one is bigger than which route is better than which phenomenon is unfolding faster than which. Okay. So we can create an animation, but sometimes an animation is not the best choice, and I'll show you why. So what you're watching here is a relatively simple machine. This is an undamped pendulum, meaning we have a simple box here. We have an arm that's hanging, and the arm is just passively swinging back and forth. It's a very simple mechanical system that's studied in first-year engineering courses. And generally speaking, we can describe an undamped pendulum with just two variables, angle and angular velocity. Let's look at angle. So angle is basically what is the angle of the arm relative to vertical. So if the arm is straight down, it has a degree of 0. If the arm is swinging to the right, it has a positive angle, and if it's swinging to the left, if it's to the left of vertical, it has a negative value. So at any instantaneous point in time, we can say, for example, the arm at this point has an angle of about minus 10 degrees. Of course, that angle itself is changing over time, and usually we're interested not just in the angle of the arm, but how fast the arm is moving. So that we can represent as degrees per second, for example. Positive angular velocity means it's moving quickly to the right. Negative angular velocity means it's moving to the left. And a 0 angular velocity means the arm is not moving at all. What can you tell me about the relationship between angle and angular velocity by watching the short video? How are they related? So if angle is high, can you say something about angular velocity? If angle is low, meaning it's close to zero, can you say something about angular velocity? Are these two variables related to one another? What is the relationship between angle and angular velocity in this relatively simple machine? So high angle means low velocity. Yep, makes sense, right? So as the arm reaches the top of its swing on either side, velocity is going to slow down to zero, and then it's going to alternate and start to increase in velocity. Can we say anything more specific about that? So most of us can see that, or maybe you know that already about undamped pendula, but you can kind of see it in this video. You can see that the arm speeds up when it reaches the bottom of its swing and slows down when it reaches the top of its swing. But it's hard to say anything in more detail just by watching this video. You remember a few weeks ago we talked about the pros and cons of streamy versus chunky data. This is streamy data. We're streaming a video, which is useful. You can learn something about the undamped pendulum from this streamy data. But we're also not able to extract a lot of details until we switch to a chunky visualization or a static image like this one here. Here's one way of plotting this information. You'll notice we have two panels. We have time in seconds on the horizontal axis, so we're going up to almost 300 seconds, so about 5 minutes worth of data, where this arm is swinging back and forth. The vertical axis in the lower panel is angular velocity. So what is the velocity of the arm in degrees per second at that time? The upper panel is showing change in angle over this 5-minute period. And immediately, or hopefully, you can extract a little bit more detail about the behavior of this pendulum from this picture than from the video you just saw. What is some of that additional detail about this pendulum that you can extract from this visualization? It's actually hard to see from this picture, at least, that high angle means low velocity and vice versa. But there are some other aspects of the machine that you should be able to note from this picture. Let's start with the angle panel. You'll notice when the pendulum starts, it's ranging between about positive 150, which is almost all the way to the top. So 180 degrees would be up. So about positive 150, and then rotating all the way around to about minus 150. When we start the pendulum swinging, remember this is a passive pendulum. There is no motor that is driving the movement of the arm. It is just passively swinging. How does the swing change over this 5-minute period? Why doesn't it keep swinging between positive 150 and minus 150? As David mentions, there's friction here, so this is not a frictionless system. So the connection of the arm to the box, there's a little bit of friction that is slowing the arm and causing it to reduce the range of motion. So you can see the height and depth of these lines is decreasing over time. So friction is causing the range of motion to decrease. But we can see even an additional detail. How is it decreasing? Is it decreasing linearly? Or is something else going on here? What can we learn about the friction in the system just by looking at this picture? If you look carefully, you'll notice that the range of motion drops faster in the first 50 seconds here or so when the range is high and when the speed is high. So as this thing is swinging with high velocity around a large range, there is more friction, causing it to slow and narrow its range of motion faster. And then that rate of slowing itself decreases and becomes more flat as time goes on. This is a hint that that friction is proportional to velocity in this case. This is something that's well known in mechanics, but if you think or reason about this picture, we could ask the hypothesis, how is friction affecting the system? It's affecting it proportionally to velocity. Okay, this is just one way of plotting this data. It's a little bit inefficient because we have to sort of jump back and forth between these two plots. If we're thinking about friction, we can see that the rate of motion decreases faster. There's more friction when angular velocity is greater. So we got to sort of jump our eyes back and forth. You remember our cartoon example about spot the difference between the two cartoons from last time. Could we plot this data in a different way where we're going to take these two visualizations and compress them into one? Can do that using a phase diagram. The phase diagram, remember that we have these two variables. We have angle and angular velocity. We put angle on the horizontal axis and angular velocity on the vertical axis. At a given point in time, so when we start this experiment, when we took the arm and rotated it to 150 degrees and let go of that arm, at that moment in time, we can record two numbers. What is the angle and what is the angular velocity? So we get those two numbers, we find that position, we use those two numbers as the x and y coordinate in this two-dimensional plane, go to that point and draw a dot. We then let the system run for a little bit, and at the next point in time, so this is probably not 1 second, but maybe 0.1 second later, at some point in time, those two numbers have changed, which means we've moved to a new x and y coordinate in this 2D plane. Put another dot, let the system run forward in time, get those two numbers again, draw another dot, and in a phase diagram, we end up drawing a line in 2 dimensions here, and that line represents a trajectory which shows how these two variables change, angle and angular velocity, as time runs forward. You'll notice that in this case, in this particular case, by drawing the exact same data, we took this data and just drew it in a different way, it suddenly revealed an additional detail about the system. What is that additional detail? We're not drawing any new data here. It's exactly the same data that we drew here. We're just drawing it in a different way, and it suddenly revealed an additional detail. What is it? What can you tell me about this machine that wasn't obvious in the previous visualization or in the movie? You'll notice there's this hiccuping vertical line here at about minus 50 degrees. And it always shows up at minus 50 degrees regardless of the angular velocity. It doesn't matter if the arm is rotating quickly clockwise, negative angular velocity, or rotating clockwise, positive angular velocity. It always shows up. Suddenly there's a little bit of a hiccup here. Why do you think that might be? You can watch the video again. You can't see that hiccup here. It's so slight, but we see it in the data. Any ideas? So it turns out that we placed a sensor inside this box that's recording angle and angular velocity. And so we're recording it automatically. It turns out that there's a little metal bar that's basically holding the vertical bar, and there was a little notch in that bar, a little bite out of the bar, and the sensor was looking at the rotation of that bar. And so it was basically the sensor was having a hard time recording minus 50 when that little bite or that little imperfection in the metal came in front of the sensor. So there's a little mechanical imperfection that shows up as a hiccup in the sensor reading at a particular point in time. There's a little bit of an error in our signal. So again, that detail doesn't matter for our purposes, but it does matter, but it does tell us that different ways of visualizing the data can help us expose various details that are in that data set that may be unobvious if we draw the data in a different way or simply watch a video of that data. This may become important to you when your user is trying to learn ASL digits over the device and they want to know how well or how poorly they're doing. They may want to know whether they're getting better or worse over time. Now we're talking about pictures of verbs. We're talking about a particular process, which is the learning process, that is changing over time. How might we create visualizations to help our user understand that they're getting better, but maybe they're getting better more slowly as they get better at a given digit? You're going to have a lot of opportunity towards the end of this course to create visualizations that expose different aspects of this particular process of learning ASL digits. Okay, so we mentioned this phase diagram. This phase diagram here, which is drawing a trajectory of how two variables change over time. I drew this example from some of my own past research where we were playing with this very simple machine. And we wanted, in this case, the computer to learn, basically learn how this machine works. And what we did was we just gave this computer this information. And the computer had to generate equations. You'll notice that in purple here, the computer generated this equation here, which we won't go into math too much, but this equation is the computer's guess about how angle changes over time. It also made a guess about this equation, and this equation is the computer's guess about how angular velocity changes over time. So I can ask you the same question here by looking at this raw data. How is angle and angular velocity changing? And I want you to write down an equation that describes how this angle is changing over time. And I want you to write down a second equation, which is how angular velocity is changing over time. You might write down those equations, and those equations may be more or less correct. In this case, the computer generated 11 different pairs of equations. This pair of equations here, another pair of equations, another pair, fourth pair, fifth, sixth, seventh, eighth, ninth, 10th, 11th pair of equations. We then wanted to know how good those guesses were. The computer, basically, it's an AI that's trying to generate equations to describe data. How good are these equations? I don't know about you, but I can't read these equations and know how accurate they are. So we took in this case, we took the computer's equations and we drew a phase diagram from them. We put in an initial angle and angular velocity and then pushed those through the equations, and the equations spat out new angles and angular velocities according to those equations, and that painted a line in the phase diagram. We went to a new initial angle and angular velocity. We didn't send it to the machine, we sent it to the equations, which produced another line. So we have 11 visualizations here of how good the computer is at guessing the actual phase diagram from the actual machine. Which of these 11 pairs of equations was the best one, based on looking at these phase diagrams? First one, second one, third one, fourth one, fifth one, sixth. Which of these 11 equation pairs is most accurate, is closest to the reality of the actual system. Okay, we're running out of time here, so it's this one here. The visual correspondence between these two is pretty close. And it turns out that this pair of equations was closer to reality than these other. Okay, this was just a last example to show, in this case, we were performing a particular activity, which is to try and understand how accurate a computer's guess is about an explanation for the system. And we created particular visualizations, in this case phase diagrams, for us, the human observers, to be able to see at a glance which of these equation pairs was better than which other equation pairs. I'll stop there. You have a quiz due tonight. You are starting in hopefully on Deliverable 5. Have a good rest of your day, and I will see you back here Thursday morning. Thanks, everybody.